So now we're moving to Maria Gabriela Navarro, and she's going to talk about about microlensing events in the VVV, current status of future work.
Okay, so maybe some of you don't know me yet. My name is Maria Gabriela Navarro. I'm a PhD student in Chile and Italy. So the first part of my thesis is the searching for microlensing events in the galactic bulge using the VVV data. This is not working. Okay, so basically, I think most of you know, but I will briefly explain what is a microlensing event. So when you are observing a star and another object passes near the line of sight between the observer and the background source, you will see a deflection of the light. You will see multiple images that are formed from this configuration. But in the case of short scales, let's say if we're observing toward the galactic center, for example, we are not able to detect these multiple images, so we will see just an increase in the apparent brightness of the background source. So this is what we are searching now. So basically, the motivation of this study is that if we observe here, this is a work from O group, and they just show the amount of microlensing events that they found in the galactic bulge. You can see that the red color are the areas with higher amounts of microlensing events. So the point is that as we approach the galactic center, we expect to find a lot of them. But although it's an optical survey, so that's why with the VVV we can try to find some of them in this area. This is another study. This is a theoretical study of the optical depth toward the galactic center for different surveys. And you can see in the K band, we expect to find a lot of them. Again, I will go back to that later. So I decided to study the very center of the galaxy, let's say the area of the bulge. And this is the reddening map of Oscar Gonzalez and collaborators. And I just wanted to show you that the area that we are focusing our studies is the most reddened area of the galaxy. So let's say this is 0, and we study the plus minus 10 degrees in the very center. The PSF photometry that we are using is the one that Rodrigo Contreras Ramos published some years ago. So just to show you a picture of this area. So the important point of this is that we find a lot of stars there. So the probability to find microlensing events is even higher. So in numbers, we analyzed 20 square degrees, more or less. We have from 73 to 104 epochs in the very center. In total, we have 10 to the 7 point sources, and the limit in magnitude, probably most of you know that is more or less 18 in the K band. So basically what we did is to compute like a semi-automated algorithm. So the idea was to just draw some lines in every of the light curves, and then I tried to find like a connection between these lines, trying to reproduce a microlensing event. In this case, all the procedure was searching for PSPL, that is the point source and point lens events. So we are not searching for binaries, and so this is for the future. Then I will mention about it. So you can see here an example. So this is the searching procedure that I created. So and then after writing these lines to all of the 10 to the 7 light curves, we obtain something like this. Using the standard microlensing model, we try to fit these light curves, and then we decide if they're a microlensing event or not. You can see there that this is clearly a microlensing event, right? So then after this step, we analyze every light curve, and we put some constraints. So you can see that in the constraints, the most important one is the symmetry, in the sense that we are searching for PSPL, so we didn't include the binaries in our sample. Then the number of data points is 20 minimum. The baselines should be constant. Then the fitting procedure should be okay. And the time scale, we put a constraint in 200 days. So then, just in order to check the results, what we did is to search, because most of you know how is the VVV observing. Maren is a specialist in this, but what I understand is that this is the camera. These are the detectors. And in order to fill the gaps between the detectors, they are moving the telescope. So this is more or less the idea. So what I did is like to search in this area where we have a superposition of different observations in different foci. So in those areas, we expect to find, if there is a microlensing event there, we will find it twice, right? So we try to find repeated microlensing events. So those are the constraints that we applied. So the distance should be less than 2 arcseconds. The time of maximum amplification should be less than 7 days. And the magnitude should be less than 0.15. And we found some of them. For example, in this case, both are almost in the same area. Both have the same time of maximum amplification. And the light curves look similar. So probably this is the same event detected twice. And if we compute both light curves at the same time, you have this. So then we decided to merge both light curves so we can constrain the parameters better. And you can see this is the final result. So actually this is a repeated one. So this is just to test the searching procedure. So I will go back now to the results. So first, 2 years ago, we searched in the 3 innermost tiles. And we found 182 microlensing events in the very, very center. So you can see here, this is the center of the galaxy, and all these different red squares are the microlensing events that we found. And I mean, if we do a cross match with the other surveys that are searching for microlensing events, we are not going to find anything because this area was hidden so far. So it's quite interesting to continue searching there. So we decided to extend the area. And this is a nice plot because you can see oval group, that is the biggest group searching for microlensing events. Then you can see the MOA results. So the blue crosses are oval microlensing events between 2010 and 2015. Then you can see some light blue crosses that are MOA. And the VVV are the magenta crosses. So it's very important in this area to search there to like complete the area on the galactic patch. So just in numbers to show you more or less what we did. So we started from 10 to the 7 time series. Then with the first method, we reached like 10 to the 4 more or less light curves. And then we observed every of the light curves and we got the final sample. So this is a very time consuming part of the procedure. So again, just to check if everything was working well, because since we don't have any superposition, we cannot compare to other results. We fitted our light curves with our searching procedure. We fitted some oval light curves, and we obtained the same parameters. So you can see here two of the light curves that we found with VVV, and you can see with oval they have more data points, but we can constrain anyway quite well the parameters. Okay, then the most important parameter that we can constrain from the light curve of a microlensing event is the timescale, because the timescale has a physical information. So the timescale is related to the mass, the transfer velocity, and the relative distance of the configuration of the microlensing event. So we can kind of relate the timescale with the mass. So in general, long timescale events suggest the presence of black holes, and very short timescale events suggest the presence of planets. So here you can see the distribution of the 630 microlensing events that we found, and the big squares are related to black hole candidates, let's say, and the very small squares to I don't know planets in this case. I will talk about this later, but you can see that here is clear. if we just show the very long time scale events and very short time scale events, we see that the long time scale events are quite distributed, like in all the area, and the short time scale events are computed, are more concentrated in the center. But this can be related to the observations of VVV because we have more observations in the very center. So that's why I think we can find more short time scale events there. Any questions so far? Yes.
Just a simple one. Is there a degeneracy of the long time scale events between disk microlensing events where you have two stars which have a relatively small relative velocity and take a long time?
Yeah.
Could they be confused with black holes?
Yeah, I know. Yeah, this is an
I'm asking because I don't know much about this. So.
Yeah. Actually, we kind of relate the time scale with the mass, but we cannot say this like all the time. In general, if the source is in the bulge and the lens is in the middle between us and the source, in general, if we find a very long time scale event, let's say 1 year, it's a black hole. Like the probability is quite high. But yeah, the problem is that we need the transfer velocities and the relative distances. So it's not like a direct. I mean, we cannot assume that the long time scale events are black holes.
You can put constraints. Minimal and maximum.
We can compute a distribution, a density, a probability distribution where you can see, depending on the distance of the lens, you can see what will be the mass. And then I will talk about it now that we can use the red clamp stars to try to analyze better the results. So yeah, it's an important point. I mean, we cannot just say this. It's an approximation. Not the first time.
I have a question, if you wouldn't mind.
Yeah.
Yeah. So just on that previous plot, on the southern side of your slice, forward one.
Another one before?
No. Go forward a few slides. Actually. So I have one for this one. You go.
Light curve.
The light curve?
Yes. So what is the blue curve on that top right, top left?
Okay. Yeah, so we fitted the light curve taking into account the blending. So one is a model including the blending parameter and the other one is without the blending. So the blending is when you have this contamination of the light of a star that is nearby.
Oh, okay, right. So there's blending involved in this one.
Yeah, it's just blending, so that's why you have some differences there.
These are the same events left and right. Is that correct?
Sorry?
The left and oh no, these aren't all. These aren't. Are these the same events on the left and right?
No. They are not the same events. Sorry, no.
Right.
I just want, yeah, there are different events. I just trying to check if the parameters that my model is giving me are correct. So I use my model to compute the parameters in oval light curves, and then I compare with oval parameters.
Oh, okay. No, I follow you now. Sorry, I thought you had duplicate events in VVV and ogle, and we're comparing.
Yeah, no. I mean, so far we don't have any cross match with ogle.
Ah, I see. Okay.
Mm-hmm.
So if you go forward 2 more slides, I think I have one more question.
Okay.
So
this one?
On the top plot on the left, on the right, on the southern side of the slice, maybe it's just my eyes, but you have more events there. Is that significant? Is there any reason for that?
Yes, actually, I will go back to this now because we have the distribution of number of microlensing events that we found more in negative longitudes. Yeah. And we think that maybe this is because of the inclination of the bar. So we expect this result actually.
Yeah. Okay.
Mm-hmm. You're welcome. So then the idea is to compute the optical depth. So Chris Beck did it in a theoretical point of view, and you can see MOA. They are trying to compute it, but they cannot reach the very center. So that's why I think it's very important to use the VVV data and then to try to reach the very center and to see what's happening there. So then I will briefly talk about the efficiency because it's not very, very important, but an important thing that we noticed is that here are the types, the different types that we analyzed, and here is the time of the 5 years of observations. And here you have the observations, and here you have the events that we found. So both plots are pretty similar. So this is, this is just telling us that when we have like more observations, we have more events. This is normal, but we have to correct our final sample by this problem with the efficiency. So we corrected by efficiency, that sampling efficiency. So what we did is to create fake microlensing events with Monte Carlo simulations, and then with the observation of the VVV, we check if we can reproduce them. So this is a very confusing plot, but the most important thing is that I created 1,000 events of 100 days of time scale. And then with the observations of the VVV that you can see here, that we have a lot of vertical lines that are the observations of the VVV, we check if we detect them or not, okay? We did this for different time scales because of course the short time scale events, we are not going to detect them if we have like a lot of time between observations. So this is the result. We did this for every tile. So you can see, this is very important because the short time scale events that are here, the VVV is not very efficient discovering them, but the long time scale events are, we're quite good doing it. So this is important, for example, for some people that want to search for planets. We are not very good at planets, but we can complement their work in the long time scale area. And then we have to take into account the photometric efficiency. And for this, we use the completeness map of Elena Valenti. So you can see that we are more incomplete store at the center. This is for red clamp stars. So we took into account both effects, and then we selected, this is a question that you did before. So we selected the red clamp stars because we can assume that the red clamp are going to be located in the center of the sources. So then it's better, it's more clean to use this sample. So we have 290 red clamp sources. And then we compute the distribution. So this is the longitude, and this is the number of events. This is the number of red clamp stars. This is the number of stars in total. And this is the event rate. So you can see that we have, of course, more microlensing events towards the galactic center, but then we found an asymmetry. We found 60% more stars in negative longitudes. And we think that maybe this is due to the inclination of the bar. And then if we compute the time scale distribution, that is simply the time scale histogram, we find a peak in around 20 days that is a little bit shorter than the normal, but this is just trying to tell us the different populations that we have. So this is the long time scale tail where we can expect to find black holes, for example, or neutron stars. And here are the planets, and this is the main sequence stars. So this is in agreement with previous studies, but this is the first time we do it in the plane. So it's very interesting to compare the results. Then if we compare this with the model of Chris Beck, we can see that we found a little bit more of long time scale events. So this is interesting then. So these are all the light curves that we found. And this is an animation, a very nice animation that Joyce did. So you can see here the light curves in the different, in all the time of the VVV. And you can see a real image of the galaxy, and you can see the flashes of the microlensing events in the specific position where it happened. And it's really nice because then you can see here, for example, that you have more events in the galactic center. You can see that we have some moments of a greater amount of events that was when the VVV was observing more. And so this is a nice animation that can show all the results that I showed you before. So if you didn't pay attention, this can explain everything actually. So then this is new results. So I include, like, please not taking picture of this. So what we did now is to complete the other part in order to have a superposition with the other surveys. So we found we have 360 events in all of these these red dots, and 70 are cross-matched with OGO. So this is the new results. And here you can see the CMB. So at the end, we did more or less the same procedure. This is very important. You can see, Javier talked about this before. So you can see the different color magnitudes diagrams of the different tiles, and you can see that the central one is very extended. So what I wanted to show you is that we corrected by efficiency the distribution of number of events, and in this case we found that the number of events is increased stronger than in the longitude dependence. So this is the very important result because it's the first time that we can do a latitude analysis, right? So this is the complete sample. This is the red thumb sample. The dotted lines is the raw results, the raw distribution, and the field lines is corrected by photometric efficiency. So you can see that the increase is very, very high, and this is the first time that we can detect this. So this can be important for the W1st in the future. And then what we did is this is the distribution, the gray is the distribution of OGO. The black histogram is the raw distribution of VVV. So we scale our distribution to OGO in the superposition area, and then we corrected it. And it's very nice because we found that here we expect to find 13,000 of events. So it's a huge amount of events if we take into account that the VVV was not created for microlensing events, but if we search with W1st or something like this in the future, even U-third as well, they will find a lot in this area. So it's very, very interesting. And then if we compute the same distribution, but if we limit the area, okay, the area of plus minus 3.7, 3.9, we can see that this is the latitude distribution, the red one, and the longitude distribution is the gray. So you can see that the full width half maximum is wider in the longitude area, in the longitude dependence. So this is the most important result I think from this new paper. And this is the first time that we can compare the distribution of microlensing events in the different axes of the galaxy. So this is another movie. This is a new one. And this is exactly the same. We are showing the light curves, and here you can see the latitude distribution. So in this movie, it's nice because it's even clearer. Something is going on with that. So it's even clearer that we have way more events in the very center of the galaxy, and then in the upper and down part, we have less. So you can see the concentration of the flashes is in the very center. So this is very nice. Again, Joyce did it. It was ready yesterday, so this is a very preliminary animation. And among other results, for example, if we compute the timescale distribution in the different longitudes, so this is the longitude greater than 6, between 2 and 6, this is the central part, and this is the negative area. So you can see that the mean timescale decreased towards the very center, right? This is the first time that we can do it again. So this can tell us something about the population of lenses that we have towards the galactic center. I mean, we have to work on it, but it's a very interesting new result that we have. And then among other results, we found 2,000 second quality events. So you can see here, for example, this is a clear microlensing event, but we don't have any information in the other side of the light curve, so we cannot compute well the time scale. So we left them like apart from our sample, but it's interesting to see if we can do something with them. We found some very short timescale events. So this is one, for example. As I said before, we don't expect to find a lot with VVV, but we found some. So it's very nice to see if there are, maybe can be free floating planets or something very small. And about parallax, when we have a very long time scale event, we have to take into account that the Earth is moving around the sun. So we have parallax effect in the very long time scale events. And in that case, you see an asymmetry in the distribution, an asymmetry in the light curve, in the event. So here, this is an oval event with parallax. So you can see the green one is the standard Microlensing model, and the red one is the parallax. And in the residuals, you see that is this parallax wall is super clear. And we found some of them. So you can see here, this is the normal standard Microlensing model. And then if you complete the residuals, you see that this is a very strong parallax effect. And those are very interesting because they are these black hole candidates. So it's very interesting. We found some of them. And we expect to find a lot of stellar mass black holes in the very center. Then some binaries, for example, you can see this is quite strange. You can see some points there. But if you fit this with a binary model, you can see that it's pretty good. And this is a binary, a binary Microlensing event. So we have a lot of them as well. I will skip there. And for the future work, as I mentioned before, this work is very important for WFIRST because they didn't know in the past how was the distribution of Microlensing in the very center. So this is the area that we cover, and this is the area proposed for WFIRST. So we are trying to tell them that if they move towards the very center, maybe they will find way more Microlensing events there. I will skip this. And we are doing now, we are using machine learning. We are trying to extend the sample. We are going to extend the area. So we have we are creating a training set with a data cadence that this is important for VVV. So we are trying to detect Microlensing events in a faster way, and maybe we can do this for the whole bulge and for the whole disk. So yeah, so then maybe we can use VVVX data to complete the sample. And that's it. Thank you.
We have time for a couple of quick questions. Yeah.
Just to ask about the black holes. I mean, can you verify any of them by looking at them in X-rays, for example, with NICER or Chandra? Or...
Yeah, we can. I mean, we can try to do it. The problem of those is that they are isolated stellar mass black holes. So the difficult part is to confirm them. So what we can do actually is to wait, and this can lens another star, for example, or we can, yeah, we can try to observe in another wavelength. We have some ideas there, but the problem is that they passed already. So
okay, so by definition, they have to be isolated, or you'd see the companion.
Yeah.
Yeah. Okay. So.
Yeah. So the other thing that is interesting to do is astrometry. If you do the astrometric measurements during the long time scale event, you can compute the mass.
Sure.
And the problem is that they already passed. So
yeah.
Just a comment, when you correct your number of events for photometric completeness, just keep in mind that the completeness test we did for Elena is based on detector 12 only.
Yeah.
Okay, so that is I don't know whether your sources, they probably fall in all.
Yeah, no, we have to take into account that this is a very, this is, I mean, we can apply this correction for just red clamps probably, right? Or...
No, it's just that the detectors are different.
Okay. Yeah, this is important. I mean, we can try to do it better. If you have any idea, it's very welcome.
No, it would be nice to, if you want to fine tune, if you had a completeness test for different detector. I mean, they were very well specified.
Yeah.
Which detector has, how much they are different to do the test for the least efficient one and see, okay, how wide is the difference to have at least some error margin. What you might have missed.
Yeah, it's interesting to
how far you are off in your completeness correction.
Yeah. Thank you.
Okay. Yep. That's one.
So can you convert your event rate into some estimate of the number density of black holes along the line of sight?
I really don't know. I don't know that, I don't know the answer. I mean, we are using models now. There are a lot of models. There are a lot of papers coming out now that they say that we expect like 10,000 stellar mass black holes in this area. So, I mean, the probability that we have some in VVV is pretty high. But I don't know how can we estimate from the, I mean, we can use some models, but then the problem is that we are, again, we have problems because we are detecting sources on the far disk, so we cannot just use the timescale distribution to compute the stellar population that we expect to find there. Yeah.
Okay.
So it's contaminated. Yeah, it's contaminated our timescale distribution now, I think. I don't know.
Yeah, we need pretty fancy model.
Yeah, we need something different now. Yeah.
But now it can be done because now they are the observations to test the models. Before they were not.
Fantastic.
So you mentioned that one implication might be to try to convince the W-first people to move.
To move it, yeah.
Now, your light curves are all K-band light curves, right?
Yeah, okay, they have to include the
So
K.
are all the are all the sources that are detected in J and H, or what fraction are seen in J and H? And
Most of them, I would say, because we have just one observation, so we use actually in the MD, I showed that we have some,
the desirability to move up depends on how detectable they are
yeah,
at shorter wavelengths.
so you can see here this line, and this is just because we don't have information in the J band, for example, so I just computed the limit of the survey. So this is events with the J magnitude, without the J magnitude, so I had to compute it somehow.
And that was what fraction?
Well, I don't know exactly. It's a good question, but it's not an important fraction of them.